So, hello everyone. Can you hear me? Can you confirm any one of you? Hello.
Yes, sir. Hearing, sir.
Okay, okay. Actually, there is some problem with my headphone, I think, so I have to use my laptop's microphone. That's why I asked. Okay, thank you. So, welcome to the third class of the third tutorial of the introduction to classical mechanics. So, last day we have done some problem of Lagrangian method. Now, today we will discuss some more problem on the Hamiltonian at first, and then we will do one or two very easy problem from the small oscillations, and the details of the small oscillation will be done in the next class. As I also see that the material of the small oscillation is not was not uploaded in the third week. That's why we will do it in the next week. So, coming to the Lagrangian and Hamiltonian thing. So, as you all know, that Lagrangian is can be expressed as q dot and t. This is a very small recap. So, if we take the time derivative, that will be del L del Qy dqj dt plus del L del Qj dot dqj dot dt plus del L del t. Now, this particular term, that is that del L del Qi term, if we replaced it using the Lagrangian equation, so that will give us d dt of del L del Qj dot, and dqj dt is Qj dot, I think Qj dot plus del L del Qj dot dqj dot dt plus del L del t. It has already been done, so I am just recapitulating it. So it will give you that d dt of Qj dot del L del Qj plus del L del t. Okay, now this can also be written in the form of d dt of Qj dot del L del Qj dot minus L plus del L del t equals to 0. So, this from this line to this line I have not explicitly written down it. You can do it, because the at first this d dt will work on this first term, and then the second term. Accordingly, we have to eliminate the second term, which will come by the differentiation. So you will get this particular term. Now the point is, this particular term is called as Hamiltonian of the system. So that is h. Now that's why we can write it dh dt plus del L del t equals to 0. That means dh dt is equals to minus del L del t. Now suppose if L is not a function of LT, not equals to a function of LT, then this del L del T will be 0 and your dH dt will be equals to 0. That will give you H is a constant. That means if your Lagrangian does not explicitly depend on time, then your Hamiltonian will be a conserved quantity of time. So okay, now, and remember this is the Hamiltonian. Okay, now we will do some problem using this Hamiltonian. So okay, let us first do another mathematical derivation. So our Hamiltonian is, as I see shown here, this del L del Qj term is Qj dot term is actually the momentum Pj. So it can be written as Qj dot Pj minus L of Qj dot and T. Now if we took the total differential of this particular element, so that will be Qj dot dPj plus Pj dQj dot minus, now it will act on L, del L del Qj dQj minus del L del Qj dot dQj dot, sorry, and minus that time is there, del L del T dt. Okay, now okay, now you can see that we can write this particular expression in terms of like this Qj dPj, that is the first term, and another term would be okay, so you can see this is the Pj dQj dot term, and this one is del L del Qj dot dQj dot. So del L del Qj dot is actually the Pj. So this term will cancel out this term and it will be Pj dot dQj minus del L del T dt. Here I have written this del L del Qj term, del L del Qj is as Pj dot. Okay, so this is the dH. Now an interesting thing will come out if we write H. So just a second, so H is QPT. Yes, so also so remember this particular expression. Okay, we will need this. Now H is itself, it is a function of Q, P and T. So this, if we express H in terms of Lagrangian, using that I am getting this differential total differential of Hamiltonian like this quantity. Now we are going through another approach where the H is a function of Q, P and T. So if we take dH here, that will give you del H del Qj dQj plus del H del Pj dPj plus del H del T dt. So why we have done that? Actually now we will compare these two different equations. So this is equation 1, this is equation 2. Now we will actually compare the similar terms, like this term here we will compare this term with this term because it is the term associated with the dPj. So that will give us Qj dot is actually dH by dPj. And if we also compare this first term with this second term which is associated with dQj, it will give you Pj dot as minus of del H del Qj. So here is a minus sign, that's why this minus sign is coming in this expression. And remember, this minus sign is the most important minus sign in the whole classical mechanics, so never forget that. And if we compare this time term, then it will give me as del L del T is equals to minus del H del T. So these three are actually the equation of Hamiltonian. So remember, Qj dot is del H del Pj, Pj dot is minus del H del Qj, and this one. Now suppose you have a system of like a harmonic oscillator, and it is not a function of time. Thus in that case your age will be a constant of time, and age will be also the total total energy of the particular system. So if you can write your age as a total energy of the particular system, and by differentiating that particular age with respect to the momentum and with respect to the coordinate, then you will get that Qj dot and Pj dot time. So in some situation in physics, this is more favorable than the Lagrangian method, this Hamiltonian method. So using these two very simplest equation, you can tell many things about a particular system, physical system. So that's why we will do a very simple example based on this two equation, which is the canonical equation of Hamiltonian. So these three are canonical equation of Hamilton. Okay. Now let us suppose a situation where a particle, so it is an example. So a particle moves under the influence of a central force. Okay, so a particle is under a central force. That means suppose this is the orbit of the planet. Suppose the particle is a planet, and a central force which is acting towards the center, it is the center, which is the force due to the gravitation, that is gmm by r square if it is small m and it is capital M. So gmm by r square is a type of central example of a central force. That's why I give that example. So let us come to the problem. Okay, now at first we will do the write the Lagrangian of this system. So the Lagrangian is actually this one, t minus b, because and there is no explicit time dependence of Lagrangian in this particular system. So t can be written as half m, and if I use r and theta coordinates, so suppose this is the r from the center and this is the theta or phi, whatever, then the kinetic term will be half m r dot square plus r square phi dot square, right, minus v, where v, the potential, is a function of r because it is the force, and if you do the derivative of this force, that will give you the potential. Okay, so that is a function of r. Now we will calculate the momentum of this along the radial distance. So from the Lagrangian method, I will do this problem both in Lagrangian and the Hamiltonian method. Okay, so this PR is actually del r dot, because you know that in the Lagrangian system Pj is actually dl del Qj dot. So the similar thing. Now okay, so del L del r dot, so it will give you the mr dot. Similarly p phi will give you will come from del L del phi dot, and that will come as mr square phi dot. So our PR is mr dot and p phi is mr square phi dot. Okay, now if we write this equation in terms of, I am expressing the r dot in terms of PR, and here the phi dot, that is so the phi dot is p phi by m r square. This phi is in the here. Okay, so r dot and phi dot are these two. Now we will calculate the Hamiltonian. So Hamiltonian was Pj qj dot minus L. Now our pj is actually the pr r dot plus p phi phi dot minus L. So L we have already written as r square phi dot s square minus vr. So this is the same thing as this. Now if we put our r dot and phi dot here, and yes, so it will give us pr. R dot means another pr by m plus p phi, and phi dot means p phi by m r square minus this total term. I am not writing that term. So that will give you, I mean this is the L. Okay, so p r square by m plus p phi square by m r square minus L. Now in this L also we will substitute r dot and phi dot in terms of pr and p phi. So one question you may ask, why I am substituting my r dot and phi dot in the expression of h? Because as you know that h is always expressed as a function of q, p and t, never q, q dot and t, whereas L is expressed as q, q dot and t. So that's why we have to replace this q dot to this p when we are expressing our Hamiltonian from the Lagrangian. So that's why all the q dot will be transferred to p. Now similarly, if we put pr by m square plus r square p phi by m r square whole square minus vr. Okay, so this. Now if you do this, this half here will be also a half. This half is multiplied by both term. Okay, so here is a pr square by m, and here is a half pr square by m, so that will be pr square half pr square by m. Similarly here the term will be 2m r square, and this minus minus plus vr. Okay, so this is your Hamiltonian for that particular system when a particle is under the central force. Now, and you can see this h has been expressed in terms of q, p and t. Although there is no explicit r and phi here in the for this particular expression, only p's are here, but it will, as a general, it will be a function of q, p and t. Okay, now we will go to the other case. I mean here what I have shown you, that qj dot can be written in terms of I mean using the Hamiltonian, and pj dot can be written using the Hamiltonian. So that we will do. So what was that? Qj dot equals to del h del pj, right? Am I right? Qj dot equals to del h del pj. Yes. So from here, at first we will write the radial part, r dot, that is del h del pr, and our h is already expressed in terms of pr and p phi. So if we do the differentiation, it will give us pr by m. Okay, and similarly if we do the phi dot, that will give us p phi by m r square. Okay, so r dot and phi dot are these two. Okay, now another equation was the momentum equation, pj dot equals to minus del h del qj. So pj dot equals to minus del h del qj. So that will give us pr dot is minus del h del r. So if you do the del h del r thing, then yes, so r dependent term is here 2m. Okay, so what I have said here, so there is a r dependent term, I mean q dependent term here, the second term is q dependent. I have not said that. Okay, so if you do the integration with respect differentiation with respect to r, then you will get p phi square by m r cube, and your v is also a function of r, that means dv dr. Okay, similarly your p phi dot, that will be minus del h del phi, but you can see there are no dependence of phi in this particular Hamiltonian, because there is a r dependency term and v is a function of r only, not a phi, so that's why it will be 0. That is telling you that p phi is a constant. Okay, so and you can say that phi is also a cyclic coordinate for this particular problem. Now the thing is, suppose someone have given you the Hamiltonian, and you don't know anything about the Lagrangian of the, and you don't know the Lagrangian explicitly about the problem. I mean, you don't know the Lagrangian of this particular system, suppose this, but you know the Hamiltonian is written like this. Okay, so in that case, using this particular two equation, qz dot equals to del h del pj and pj dot equals to minus del h del qj, you can calculate the equation of motion. So here the equation of motion is pr dot, this one, I mean pr dot equals to p phi square by mr cube minus del v del r. And another important property about the system you can mention, that is the p phi dot equals to 0, that means the p phi is constant. So this is another way of studying any particular system using the Hamiltonian mechanics. And you can see this r dot we are getting as pr by m using the Hamiltonian method. The similar thing we have got using the Lagrangian method, where this equation, let's say this is the Roman 1 set of equation, r dot equals to pr by m, and this is the Roman 2 set of equation. So you can see these two set of equation are exactly similar, r dot equals to pr by m here in 1 also, here in 2 also. So this is telling you the same thing, whether you are going through the Hamiltonian method or the Lagrangian method. So these two equations, system of equations, are exactly identical. Okay, so this is the I mean use of Hamiltonian in our classical mechanics. Now one important thing that I think I should mention here, that is the difference between the Hamiltonian and Lagrangian. So till this point, anyone have any question? Okay, then we will go to the next session. Now in the derivation of this, the Lagrangian, here I have shown you that dh dt is equals to minus del L del t as a general thing. Okay, so dh dt is equals to minus del L del t. Now if L does not explicitly depends on time, that means dh by dt equals to 0, and h is a conserved quantity as a concept of time. So there we will now we will do an interesting problem. Okay, that is a simple harmonic oscillator on a uniformly, and after getting the result I will tell you the interesting fact, moving cart. Okay, so suppose this is a plane along the x-axis, and here there is a cart. Okay, so the cart is moving along the x-axis, on this particular surface, and here there is a sting and a mass system associated with this particular cart. So this is the sting and the mass system, where the mass is m and the spring constant, let it be k. Okay, so this is the thing. Now suppose that this kart is moving with the velocity of v0, that is the uniform velocity. Okay, and this point, this o is the origin of that. Now suppose this o is the origin at t equals to 0, and suppose at t equals to 0 this is the system. Okay, where the here yeah, so no, so I have to draw another figure, that's why I was trying to do it in one figure if possible. Okay, so this is the origin. Suppose this is the origin of the system, and at t equals to 0, suppose the cart was the mass, I mean the cart was in this position. Similarly, the cart was in the front wheel will be there, and the mass was in this position. So at t equals to 0, the cart is this one, and the mass was in this position, this is m, and after a time t, this cart has moved from this position to this position. Similarly, the mass have moved from this position to this position. Okay, so now this is the position of the cart at a time t, suppose. Now that's why I am removing the previous case when it was at t equals to 0. Sorry. So yeah, now so this is the situation at t equals to t, or t dash, whatever you can say. So yeah, so this is suppose o dashed when the cart was at this position at a particular at 0 time, t equals to 0. Now this distance, the displacement of the mass within the time t is let x dashed. Okay, and the cart which have also moved from the initial place, that is v0 t, because in t time with the uniform velocity v0, it will move up to v0 t distance. Okay, so it should be v0 t, this distance, sorry, v0 t, where it was the initial. Now the total distance is let x. Okay, so this is the situation. Now this x, which is the distance of the mass from this origin o, that can be written in terms of this v0 t plus the x dashed. Okay, so this is the transformation of our system, where x dash is the distance between this initial point to this mass point, and v0 t is the distance, this one. So x equals to v0 t plus x dash. Now okay, so we will write the Lagrangian now for the system. So Lagrangian, which is, and it is a one dimensional system. Suppose x dot and t, and there is no other coordinate, that is t minus v. So what is the t? T is the half m x dot square minus half k. K is the spring constant, and the spring has been contacted a distance of x minus x dash actually. So it will be x minus x dash. Yes, x minus b0. No, what I am saying. So the spring is compressed up to x dash distance. There is no x in this, because spring was at first in this position, this particular position, and it has been gone to this position. So x dash is the compression of the spring. Now this x dash can be written from this transformation equation like x minus v0 t square. Okay, so this is Lagrangian, where our dependent coordinates are x, v, and x, v is the uniform, and time. So there is no x dash dependency on this particular Lagrangian. Now okay, so E, our, and remember that the Lagrangian is a explicit function of t also here, because here is the t term. So E, that is the total energy. If we write the total energy of this particular system, that will be half f mx dot square plus half k similar x minus v0 t square. Okay, so this is our the total energy of this particular system. Now let us go to the momentum part. So p is the momentum, which is del L del x dot. So you can write is px also, as there is also only one coordinate. So del L del x dot will give you the mx dot from this expression. Okay, now if we write the Hamiltonian, that is x dot p minus L, because there is no another coordinate, so that will give you the x dot will be substituted by p by m and p. So p and px are same. I am writing whatever I want, minus the L. So L is actually, what is L was half m. If you put that x dot also, p by m square plus half k x minus v0 t square. Okay, so this is p square by 2m plus half k x minus v0 t square. Okay, yeah, so L is the total energy of the system. Yeah, so if you compare this total energy and this Hamiltonian, you can see half mx dot square plus half k x minus v0 t whole square. This is exactly same with this particular equation, where x dot has been replaced by the p, nothing different. So you can see that the in this case the Hamiltonian is the total energy of the system, right? Because H and E are same, so Hamiltonian is the total energy for this particular case. But as our L has a time dependency, that means del L del T not equals to 0, so dH dt is also not equals to 0 according to this particular equation. Here it is not equals to 0, that means it is also not equals to 0. So that means that although H is the total energy of this particular system, but it is not conserved due to explicit time dependence of t in the Lagrangian. So dH dt is not 0 for this case. Okay, so remember this thing, important. Now we will deal the same problem, I mean the same thing, but in other coordinate system. So in the first case, our coordinate system, I mean we have written everything in terms of x. No, there was no x dash dependency in our Lagrangian. Now we will write everything in terms of x dash, the same thing but just in terms of x dash. So x0 was v0 t plus x dash. Now L x dash t, okay, it will be, if you write half m x dot square was there, that means x dot will be v0 plus x dash dot, right? From this equation, if you differentiate both sides, so that square minus half k x dash square. So there is no x dependency, all x we have transferred into x dash. So it is just a transformation of coordinate, nothing else. Now another important interesting thing you can see here, the t time dependency which was in the previous case along with this term v0 t, there is no time dependency in this particular Lagrangian. Okay, so here the Lagrangian is only x and x dash, is a function of x and x dash. So that's why if you do it fully, I mean if you write it, okay, let me write it, I have written down already, from x dot square plus m x dash dot v0 plus half m v0 square, pardon me for my square sign and minus half k x dash square. So this is our L in sorry, what I have done here, it is a blunder, sorry. So it is a x dot and x dot, x dash and x dash dot, sorry for that. Okay, so it is a function of x dash dot and t, no x dependencies here. Okay. So this is the Lagrangian of this particular system, right? Let me check with my notes. Yeah, now in this situation we will also calculate the total energy, that is half mx dot square. I mean, if you write the x in terms of x dashed, you will get this result. Just put the x dot in terms of x, which we have done here, just the same thing, just replace x dot by x dash dot. So you will get x dash dot square plus m x dash dot v0 plus half m v0 square plus half k x dash square. It is the total energy in x dash coordinate, not in x coordinate. Okay, now we will calculate similarly the momentum, which is p dash, that is del L del x dash. Now L is this one. If you do this, so here the dependencies, so m x dash dot, and another one will come from this one, m v0. So that is m x dash dot plus v0. Okay, this is the p dash. Now we will write h dash. Okay, p x dash, that is x dash dot p x dash. So p x dash, so sometimes I have written p x dash and sometimes I have written p x dash. This is the same thing, no problem, just remember this. So okay, now minus L. Now L is this one, x dash and x dash dot, this L. Now if you put all this thing in proper way, so you will get half f x dash dot square minus half m v0 square plus half k x dash square. Okay, so this you will get. Now notice this equation, this particular equation. Okay, now notice this equation where it was the total energy and here the Hamiltonian. So here you can see half mx dot square, this is here, but this expression, this total expression is not similar with this expression, because there, it is obvious there are 4 terms and there are 3 terms, and this half mv square was plus, here it is minus. So by no chance it is equal to that total energy. So in this case h dash is not equal to E, that means not equal to the total energy of the system. Okay, but there is a but. So this was the L in that x dash coordinate and there is no time dependency. So the delta L delta T is equals to 0 for this particular coordinate system, which will tell you that dH dt is also 0. Okay, that means H is equal as to conserved. Okay. So just concentrate on these two different, I think you can see in that x coordinate the H Hamiltonian was the total energy, but it was not conserved, right? But in this x dash coordinate, H is not the total energy, but it is conserved. It is a conserved quantity. Okay, so this is the main thing. I mean, by the choice of generalized coordinate, the Hamiltonian actually depends on the choice of the coordinate system. So it may happen that H is conserved for one set of coordinate but it is not conserved for another set of generalized coordinate for a same problem. So this can happen. So this is the main thing which you can understand through this simple problem, that age depends on the choice of coordinate. Choice of age depends on choice of generalized coordinate. For a same problem, you can get a coordinate where age is conserved and another coordinate where age is not conserved. So this is a interesting example, and you should always remember this particular thing. Now if you want to go through this particular example, just let me know. I can give you some scanned copy of a particular book where it has been done, if you cannot understand from my presentation. So I will give you that, no problem, but please try to understand this particular thing. Okay, now any questions? Okay, so that's good. Now I will do some another thing which is a very important, which called the homogeneity of space and the conservation of linear momentum. Okay, so homogeneity of space. Homogeneity of space means if you have a system, let's say a isolated system, that is, it is not interacting with any other system. It can interact within itself, but it is an isolated system. So if your system there is any translation between your system, then there will be no change in your particular Lagrangian of the system. That means that any arbitrary displacement of the origin of the reference frame for that particular closed system, that remains unaffected. So there is no change if we change the reference point of in the particular system. So that is called the reference point. Now say it is a system of many points, and one of the points is Rj. One of the the position of a particular jth point in the system is Rj. Now if we displace this particular point, that Rj, to a arbitrary small displacement delta Rj, so according to homogeneity of space, there should not be any change in your Lagrangian. So delta Lagrangian must be 0 for that particular system. Okay, now how this will give you the conservation of linear momentum, that I will show. Okay, so now suppose that for every particle, this is a suppose system, there are many particles. Okay, so suppose it is for the sake of simplicity, for every particle the displacement is equal, that is epsilon. Let's say that it is epsilon for every particle. Okay, now what will happen? So now our delta L, which is the small displacement, small deviation of the Lagrangian, that can be written as del Rj delta Rj. Okay, so and delta Rj we have already taken as epsilon, so it will come out of the summation. So that is delta L delta Rj. Okay, and our imposing condition is delta L equals to 0. Delta L equals to 0, and epsilon is a non-zero quantity, non-zero arbitrary quantity. It can be anything. So that's why we can write delta L delta Rj, summation is there already, is equals to 0. Okay, so the delta L delta Rj is actually the Pj dot of the particular system, right? So delta L delta Rj is Pj dot. Now you can ask how this is coming. So this is this one, ddt of our Lagrangian equation, del Qj dot minus del L del Qj is equals to 0. That means ddt of del L del Qj dot equals to del L del Qj, and this particular term is Pj, Pj dot, yes. So del L del Qj, del L del Q, yeah. So this is the Pj, del L del Qj dot term is, that we can write as del L del Qj. So that means our Pj dot can be expressed as del L by del Qj. That exactly that same thing I have done here, del Q as R, so Pj dot is equals to 0. So Pj dot equals to 0 means your Pj is conserved quantity. Okay, so Pj conserved means it is telling you the conservation of linear momentum. Okay, so this is very important, the summation, the total linear momentum, not for a particular element. So the momentum for every element from I to n, the total momentum of the system will be a conserved quantity. That is the conservation of linear momentum, and it is coming from the homogeneity of space. When we are considering that arbitrary displacement will not affect that particular system, so that's why our Lagrangian will not be affected, the Lagrangian will be same, and that will give you the conservation of momentum. Similarly, the isotropy of space, where we assume there is no angular dependency on the system. I mean, if you rotate the system at a particular angle, all the properties of the system will be same. Here it was the translation, only there was no rotation for the homogeneity. But in the isotropy, you can rotate the system, but then system of particles, and there will be no effect on that rotation on the system. That is called the isotropy of space. So if you consider the isotropy of space in a similar way, so from the isotropy of space in a similar way, you can show that the angular momentum, which is Rj cross Pj for a particular system, this is conserved. So homogeneity of space will give you the linear momentum conservation, and it will, the isotropy will give you the angular momentum conservation. It is very obvious because isotropy is related with the rotation of the system, so it should give, if it should give any conservation, then it should give the angular momentum conservation. So I want to ask you to do this, try this, and if you don't get, then let me know, I will let you know how to do it. Okay, so this is two important thing, always remember. Okay, now actually now the NPTEL team has asked us to not to do the assignments before the deadline, so I will not do that third assignment today, but I will do some related problem with the assignment, which will help you to do the assignments actually, but not that exact problem I will do today. Okay, so that I will do. But now another thing, the small oscillation, very briefly I will tell. Small oscillation details will be in the next class. So what is a small what is meant by small oscillation? Now suppose you have a potential which acts like this, and you have a particle at the base of the potential, so let's say it is a V0. Okay, so if you disturb this particular particle by any outside force or anything else, so if you displaced it in this direction, this will again come into this into its original position. Similarly, if you move this into this direction, it will again come into the original position, because it is a like flow of water. as the potential is increasing from the base, it will come to the minimum potential thing, and it will come to its initial position, which is x0. So in that case it can oscillate. But suppose if you have a this type of potential when the particle is this position, and if you are displacing it with a very small distance delta x, okay, in this case there is no chance of the particle of coming back to its initial position, because it is like a flow of water from top to bottom, and it will go from the particular initial position x0 up to the minimum potential position, which may be in any other position, in any other place, but it will not come to the x0 position. That is the main point. So for the small oscillation, we need a stable equilibrium. Okay, so this there is unstable equilibrium and stable equilibrium. This denotes the unstable equilibrium, when if you perturb the system, it will not come back to the initial system, and this is called the stable equilibrium, where it will come back to the initial system. So that is the main thing of the oscillation, and it is very obvious also. This potential is like a x square potential. So if you do the dv dx, it will give you 2x, and if you do the dv dx square, it will give you 2. So 2, and similar, and by equating this dv dx to 0, that will give you the position of the stable point, that is x equals to 0. And if you put your x equals to 0 in the d2v dx square, although there is no dependency of x here, it will give you some number, and if that number is positive, that means your stable equilibrium, and if that is negative, that means the unstable equilibrium. Because like for this unstable case, v is like minus x square. So if you do dv dx, it will give you minus 2x, and d2v dx square, it will give you minus 2. So minus 2 means the negative condition, it will be satisfied, and it is the unstable equilibrium. This is very basic of the oscillations. Okay, now what is actually the small oscillation, that we will go into the next class, because there are many other things you have to know. I have seen the lectures, it is not completed yet, that's why I will not do today. But now let us do some problem which is related to your assignment. Not the although I am writing assignment 3, it is not the assignment 3, it is some related problem of assignment 3. Okay, so okay, now as you know, as sir have already done, that you know how to calculate the number of dependent or independent quantity in a particular matrix. That I will not do here, which is a very simple thing. If it is symmetric, then I think n into n plus 1 by 2, and if it is anti-symmetric, that is n into n minus 2, where n is the row into column of the matrix. N is that. Now one interesting thing we can do, like you have given a potential. Okay, so let us say Vx is equals to x square plus bx to the power 4, and it has been said that this type of potential is giving rise to some oscillations. So the question is, what is the angular frequency of this particular oscillation? How to find that for a mass angular frequency, and let's suppose there is a particle of mass m. Okay, so only the potential is given, and you have to derive the angular frequency. How to do that? Okay, now one thing I should for the very simplicity, one thing I will mention, that for oscillation, if there is oscillation, suppose this is a spring mass system, and if you stage it in this direction, it will oscillate around this initial position, stable position. Okay, so for small oscillation, the force should be directed opposite to the displacement you are doing. So if your x is in this direction, your force should be act in this direction. So force always written as minus kx, where k is the constant in this particular example, that is the spring constant. Okay, so this you should remember for small oscillation. Now very quickly I will go through, it is already 8 almost. So v is given. Now if you do the dv dx, that will d dx minus ax square plus bx4, so that will give you 2ax plus 4bx cube. Okay, and at first we will calculate the stable point del b del x equals to 0. So if you do that, minus 2ax plus 4bx cube equals to 0, this will give you two solution x square. One is x equals to 0 and another one is x equals to a by 2b root over. Actually three equation. There is a plus minus a by b, but I am taking the plus equation because it is a third order equation. So this is our extremum points. Now we have to calculate and we have to find whether it is stable equilibrium point or unstable equilibrium point. Now that will come from d2v dx square. Okay, yeah, d2v dx square. If we do this, I am not writing every step, minus 2a plus 12b x square. Okay, it will give. Now if we put x equals to 0 here, x equals to 0, that means d2v dx square is negative. That will give you the unstable equilibrium. So x equals to the unstable, there will be no oscillation around that point. And if you put a by b, so 12b a by 2b, bb, that is 4a. And here another one condition I must say at first, that a is always greater than 0. This is the given condition. So by that condition, the del 2b del x square is always positive. So x equals to a by 2b is a stable equilibrium point. Stable equilibrium point. Okay. Now, yeah. Now this equation f equals to minus kx. So f equals to minus, I am not writing in terms of component, just the value f equals to minus ax, and you know that that means df dx is equals to k. Okay, and f is also du by dx value. Not, I am not including any sign, just remember for the value, where u is the potential. So del f del x means del 2u del x square is equals to k. Okay, u or v, whatever you can say, that is, I mean, it's okay, I have used v, that's why it is better to write v. Okay, this is k. So this del 2v del x square is same as this del 2v del x square, and by putting that stable equilibrium point, we have already found the value of k is actually 4a. Okay, so our angular frequency omega will always, just a second, yeah, will always be k by m, where m is the mass of the particular of the point of the or of the system. So if we write is 4a by m, that will be 2a by m. Okay, so this is the angular frequency of the system. So it is the method how to calculate the angular frequency from a given potential. So you will find a similar type of problem in your assignment. Just the expression of potential has been given with proper condition, I mean with a and b, whether greater than 0 or less than 0 or whatever, and from that you have to calculate the angular frequency. So I think by using this method you can calculate the angular frequency of the system. Okay, now another question which can give you trouble, that is you know that you have seen that positive definite matrix, which are the positive definite matrix and which are the not positive definite matrix. Now if a matrix with multiplying with another row matrix, a column matrix, is give you a non-zero term for a non-zero column matrix. I mean, there are, if it is 3 by 3, then there will be row into column, 3 row, sorry, 3 row into 1 column. So all the 3 terms are not 0. So the which matrix we have taken, x is a non-zero matrix, or this A matrix is given in our question. So how to find that whether this A is satisfying this condition or not, or in other words, whether A is a positive definite matrix or not. So you can calculate that. I will give an example. So suppose A minus 2 minus 2 0 minus 2 1 minus 2 0 minus 2 1. Okay, I should not have chosen that red, whatever. Okay, so how you know whether it is a positive definite matrix or not? So the method is, you have to calculate, it is plus 2 minus 2 0 minus 2 1 minus 2 0 minus 2 1. Okay, you have to calculate the subdeterminant from the left side, and you need to increase from that direction. I mean, it is 1, it is 2, it is 3, suppose 3 steps. For the step 1, the determinant value is 2. Okay, for step 2, it is 2 minus 2 minus 2 1, it is the subdeterminant, and the value will be 2 plus 4 equals to 6. And for the third step, that is the whole matrix. So that will give you, if you calculate, I have calculated it, and if you calculate the determinant of A, that will give you 10. So this is greater than 0, this is greater than 0, and this is greater than 0. If all the determinant or the subdeterminant is greater than 0, then that is called a positive definite matrix. Okay, positive definite, because all the values are positive, all the values of the subdeterminant. Similarly, if you find any of the value as negative, less than 0, then that will not be a positive definite matrix. So just do this small thing, and you will get whatever is the positive definite and which one is not the positive definite. So there is a problem related to this particular there is a problem in assignment using this particular thing, so you can do that. Okay, I am not taking another example. So if you take 2 minus 2 5 minus 4 minus 2 4 5, and if you calculate with the same method, you will find that that one of the value is will be less than 0 in either step 1 or step 2 or step 3. So that it is not a positive definite matrix. Positive definite matrix. Okay, so do that. And another problem was, you have given a matrix, and you have to find the matrix which can diagonalize this particular matrix A. So this is also, I think, a very simple example. Suppose it is A33, then using that A minus lambda I, where I is the identity matrix, equals to 0. This is the characteristic equation of a matrix. So using that, you can find the lambda 1, lambda 2, and lambda 3, which are the 3 eigenvalues of this particular matrix. Now you have to calculate the eigenvector associated with these 3 eigenvalues. So how to find that? If the x is the eigenvector, then Ax is equals to lambda x. Okay, so where these are matrix, and this lambda is the scalar value of the scalar eigenvalue. So using this equation, you have to calculate the x1, x2, and x3 as the 3 eigen matrix corresponding to these 3 eigenvalues. And if you write this, I mean, column matrix, it will give you a column matrix. The x will be a column matrix. So the x1 column here, x2 column here, and x3 column here in a particular matrix, that is the matrix you want, which can diagonalize this A matrix by multiplying both sides. So it will be the inverse, and it will be, so that is the actually matrix which can diagonalize your matrix, and you can find it very easily. So this is the questions which may get you trouble, but I think these are simplest, and using this you can do the assignments, no problem will be there, I think. Okay, so today I will stop here, and if you have any other questions you can ask. Okay, then if you don't have any question, we can end the session today, and we will meet next week with the small oscillation chapter. Okay, and thank you very much for joining. Bye.